G'day everybody, my name is Magdalena Wajrak and I'm the chemistry lecturer at Edith University in Perth, Western Australia. One of the research projects that I'm involved in is the development of a voltammetric method of detection of arsenic in drinking water. And this slide here, I named this the good, the bad and the interesting of arsenic. I'm going to start off telling you about some properties of arsenic, and then I'm going to tell you about a very disturbing situation that's happening in Bangladesh, but not only in Bangladesh, other parts of the world have this problem as well, and that's arsenic in groundwater, and people are drinking that groundwater, so that's a big problem. But then I'm going to tell you something a little bit more uplifting and interesting, and that's my research where I looked at how we can develop a method that is simple, accurate, and can be implemented in the field to detect arsenic and hopefully contribute to helping people in countries such as Bangladesh where they are being affected by high concentrations of arsenic in groundwater. Now, this is an interesting picture that I've included here, and I just want to tell you a little bit about it. It's called the Arsenic Waltz. It's a little bit dark humour. What it is depicting is back in the 1800s, we didn't have chemicals that we have now. And so when ladies wanted to have a particular coloured dress, and in this case, if they wanted a green coloured dress, a chemical called copper arsenite was used to give that colour. Now, they didn't know back then how toxic arsenic was, but they would be wearing those dresses and they'd be exposing themselves to arsenic, and therefore you would have situations where people would be actually poisoned by wearing those dresses. So this picture sort of depicts the idea that it's an arsenic waltz because you're going to end up a corpse, you're going to be a skeleton after wearing that dress. So it's just a bit of a dark humour. All right, before I tell you the details of my research, I wanted to tell you a bit more about arsenic. I call this arsenic trivia. Now, the word arsenic actually comes from a Greek word, arsenikon, and it means potent or male. Interesting, isn't it? Why is male considered to be potent? I'll leave that one for you to consider. Now, the first documentation about arsenic, the discovery of arsenic, was back in 1250, and it was documented by Albertus Magnus, who was an alchemist. An alchemist was a person who would be doing chemical analysis back then, and there's a little cartoon here which depicts Albertus Magnus doing some cooking, and the way the arsenic was isolated was by heating an arsenic-rich ore. So this is a compound that contained arsenic, and together with soap, and he was able to isolate the arsenic. Quite interesting. We don't do it like that anymore. Now, the atomic number for arsenic is 33. That means it has 33 electrons. That's in its neutral state, and it has 33 protons. And in fact, it has more than 33 neutrons. It's got 42 neutrons. It has an atomic mass of 75 grams, and the physical state of arsenic in its elemental state is a steel grey brittle solid at 20 degrees Celsius, 1 atmosphere. Here's a picture of what arsenic looks like in its elemental state. Now, in compounds, arsenic can actually exist in two different oxidation states. It can be arsenic 3+ or arsenic 5+, arsenite or arsenate. And depending on which form it is in, one of them is less toxic than the other. Now, arsenic is found in group 5 of the periodic table. It is just below phosphorus. So let's have a quick look at a periodic table. Can you locate where arsenic is? So group 5, just underneath phosphorus. There it is. Now, if you have a look at where it is located, it's actually quite interesting. You might be aware of the fact that metals are on the left-hand side of the periodic table and your non-metals on the right-hand side. Now, arsenic actually fits into neither a metal or non-metal. It actually is a semi-metal. Now, what that means is, for example, it's not as conductive as a metal would be. And that's actually one of the issues why it is quite difficult to detect arsenic, particularly using voltammetry, one of the methods that I use. Now, in terms of its chemical properties, when arsenic is heated in air, it will oxidize to form arsenic trioxide, which we say is an inorganic form of arsenic. It is a very, very toxic form of arsenic. There are also other compounds of arsenic that are not as toxic. These are organic forms, and I'll talk about them a little bit later. Okay, so let's talk about the toxicity of arsenic, because it all depends on what state it is in. If it's in a mental state, it actually is non-toxic. If it's in an inorganic state, so inorganic compounds such as arsenic trioxide, they are very toxic. In fact, you only need 70 milligrams of arsenic trioxide, and that will kill an adult male. Now, what's really interesting about arsenic trioxide, apart from the fact that it is so toxic, is that it is an odorless and tasteless compound. And this is going to be very weird for me to say this, but because of those properties, it was actually the preferred poison of the 1800s. And if you can have a look at the cartoon on the right here, you can see somebody sitting in an armchair and someone else giving what looks like probably is a solution of arsenic trioxide. It actually says that arsenic's popularity as a poison was owed to the difficulty of detecting it in a corpse. And what happens is that arsenic would be metabolized in our body, it will be removed and converted into a different compound, and therefore you actually didn't know that you couldn't prove that somebody was poisoned by arsenic trioxide. So there were a lot of documented cases of people dying, and there was no way of proving that it was actually due to arsenic trioxide, but the symptoms we now know were of arsenic trioxide poisoning. So that's the bad side of arsenic. However, there are organic forms of arsenic, such as dimethyl arsenic acid, that are less toxic. And there are also compounds, organic compounds of arsenic that are therapeutic, and we use them as medication, which I'll mention later on. Now, what is it that arsenic is so toxic? Well, that's really interesting. And it all has to do with the fact where it is located in the periodic table. You see, because arsenic is in group 5 and it is right below phosphorus, what actually happens is that when it enters our body, the DNA, if you know a little bit about the DNA, I've got a diagram here to remind you, but if you look at the DNA actually contains phosphate in the backbone of the DNA. And so what can happen is that if arsenic enters the body, then it can replace the phosphorus that's in the backbone of DNA, and that results, what we say, in conformational changes. It actually changes the shape of the DNA. And changing the shape of DNA will result in the breaking of the strands of the DNA, and therefore ultimately to the damage of the DNA. And when you damage DNA, of course, that has implications in the way the cells are then created, and what can happen, of course, as we know, damage to DNA will cause, for example, cancers. Very similar to what happens when you have radiation. So if you radiate somebody, damage the DNA, it causes cancer. Now, there are two ways of identifying arsenic toxicity. What do I mean by that? Well, you can have acute arsenic poisoning, and that means high concentration of arsenic. Suddenly, you ingest a high concentration of arsenic. That will immediately cause you stomach pains, diarrhea, and I mean full-on diarrhea, shivering, swollen limbs, and ultimately will lead to death. Not a really nice way to go. Another way of having arsenic toxicity is what's called chronic toxicity. And that's when you are exposing your body to low concentrations of arsenic over an extended period of time. And this is exactly what actually has been happening in Bangladesh, where people have been exposed to relatively low concentrations of arsenic in the groundwater, but over a long period of time. And that has caused them to have skin cancers. You also end up having garlic odor on your breath. But I guess that's not something you're going to know from eating garlic, so not a very easily identifiable. But a very identifiable sign of arsenic poisoning is actually something called the Blackfoot disease. It mainly manifests itself on feet, but it can also be on hands and on the body. You can see these black marks on the body and on the feet, and that is linked to arsenic poisoning. But as I said, you also get skin cancers, and there's a diagram at the bottom here of squamous cell carcinoma and that's caused by arsenic. But of course, arsenic is not the only way you can get the squamous cell carcinoma. So really, really nasty side effects, I suppose, of arsenic toxicity. Now, apart from deliberately ingesting arsenic, how does it enter our body? Arsenic can enter our body by either inhalation, so there will be compounds of arsenic which are volatile and you can breathe those in, or of course by ingestion, whether it's deliberate or accidental. Now, it actually is very effective. Your body is very effective at absorbing arsenic, and it is distributed around the body quite rapidly. Initially, it is stored in the liver. That's where most toxic chemicals will go into. Your liver tries to eliminate, but then it goes into the kidneys, the spleen, and the lungs. So it really makes its way all around the body. So that's the bad news. But, our bodies are quite clever, and they're, apart from arsenic, we do actually expose our bodies to lots of other unfriendly chemicals. So our body is very good at eliminating those bad chemicals. It wants to protect itself. And arsenic is actually excreted from our body by a process called methylation. And that process converts arsenic into other compounds. We call them mono, di, and trimethylated compounds, which are then very easily excreted in urine. So that's the good news. The only problem is, you've got to give the body the time to excrete the arsenic. So if you have a small amount of arsenic and your body will be able to get rid of it, that's fine. But if you're continuously, ingesting more and more and more arsenic, your body won't be able to keep up. And that's where you're going to end up having problems, for example, cancers and more acute toxicity. Now, unfortunately, we are actually exposed to arsenic quite a lot. Not people know this, but arsenic is sort of everywhere. There are natural sources of arsenic, and that's from erupting volcanoes. There is also arsenic in the mineral arsenopyrite, which contains iron, arsenic, and sulfur deposits. And that is exactly what happened in Bangladesh, where those mineral deposits started to erode and released arsenic. But apart from that, human activities have contributed to us being exposed to arsenic. So, for example, smelters of copper, gold, and lead ores, they release arsenic into the atmosphere. We use arsenic in the production of pesticides and antiparasitic compounds. Interestingly enough, we also add arsenic to lead shots. We also use copper arsenate as a wood preservative. It is a green-coloured compound. So when you have, not sure if you still have those in UK, but when you have electrical poles, we still have quite a lot of them in WA, and you have to protect the wood because you've got the electrical poles, you've got the electricity lines. So those poles were painted with copper arsenate to preserve the wood. There's also arsenic used in semiconductor industry. And on the good side, we do use arsenic in medicine for treatment of certain types of cancers, such as leukemia. So there are organic forms of arsenic, as I mentioned before. There's a compound called trisenox, which is used quite successfully to treat particular forms of leukemia. So there are good aspects to arsenic. Now, apart from the human activities I've mentioned above, how else do people get exposed to arsenic? Not deliberately, but accidentally, I suppose. Well, believe it or not, if you love prawns, you will be ingesting a bit of arsenic when you're eating prawns. And also, if you do live in areas where there is arsenic in the groundwater and you're drinking the groundwater, then you will be ingesting arsenic that's in the groundwater. And like everything else, there's so many bad compounds in cigarette smoke. Arsenic is actually in there as well. So another reason why you should stop smoking or not start. And this cartoon here just shows you how, don't worry about the actual concentrations here, but it does show that there is arsenic present in prawns. And I think it says here that if you have prawns, and prawns contain 175 parts per million, and that's milligrams per litre of arsenic, and you have to ingest 25 pounds of prawns. And if you ingest that many prawns, then you would receive actually a fatal dose of arsenic. Good luck eating that many once. So why did I get interested in arsenic? Well, I sort of got interested because I was working for a company in WA that were using this instrument, and they asked me to develop a method for arsenic detection because of a need to detect arsenic in groundwater in Bangladesh. And I had no idea that there's a problem of arsenic being in groundwater. So I looked more into it, and I discovered that actually arsenic is now recognized to be one of the world's greatest environmental hazards. It actually threatens the lives of several 100 million people around the world. And we're not talking about deliberate contamination. This is all natural. So natural arsenic contamination in groundwater now affects more than 70 countries around the world. And this global picture just shows you what countries are particularly affected. And arsenic has been found, large concentrations of arsenic have been found in groundwater in America, Mexico, China has a lot of arsenic in groundwater, Vietnam, India. But of course, the biggest problem is still in Bangladesh. And believe it or not, we actually had a problem in Western Australia, just around Perth. I was involved in that research as well. So something that not many people know about, but it is a global problem. But let me tell you about the Bangladesh story, because this is a really disturbing story and quite alarming. How did this problem started? Okay, so back in the 1970s, people in Bangladesh were drinking surface water. And because surface water had diseases, nearly 250,000 people were actually dying each year due to those waterborne diseases. Now, the United Nations wanted to reduce those deaths, and they recognized that Bangladesh is quite a wet country and they have large deposits of groundwater. So they decided to build tube wells to give people access to disease-free groundwater. Now, this was a great idea. However, unfortunately, a few years later, about 10 years after that decision, where many, many millions of tube wells were built and people were drinking groundwater, doctors started noticing that a lot of people were getting unusual symptoms such as skin cancers and this black foot disease. They didn't understand where this was coming from. And it took quite a number of years to link arsenic to these symptoms that people were having. Now, the reason why it took such a long time is because no one ever thought there'd be any arsenic in that groundwater. They didn't think where would it come from. There was no industries in Bangladesh that would be generating arsenic. And the other interesting thing was that when the tube wells were first built, there was actually analysis done on the groundwater, and they tested it for many elements: copper, cadmium, lead. Lots and lots of elements were tested for, but the one element they did not test for was arsenic. Now, there were reasons for that. A, there was no need to test for arsenic, where it would come from, and B, arsenic is actually quite a difficult element to analyze. You need quite a sophisticated instrumentation. It's not very accurate always, so that was another reason why they didn't do it. Unfortunately, looking back now, they should have tested, because the geologists looked at how the geology of the formation of Bangladesh, the geological processes, excuse me, and they discovered that the source of arsenic came from the pyritic sedimentary rock that was laid down over centuries by rivers that run down from the Himalayas. So it's all natural. The arsenic was always there in the pyritic rock, but it was underground. It was not disturbed. There was no problem. However, when you start digging lots and lots and lots of wells, you've disturbed the pyritic rock. You expose it to oxygen. They started to release the arsenic, and it went into the groundwater. Very simple, actually, very simple chemistry, and yet so detrimental. So if only they did some geological studies, maybe they would have had an idea that this could happen. Now, I want to give you some statistics. This is quite an old report now, so this is back in 2004. So the numbers are probably a lot bigger now, but the World Bank's World Development Report stated that back in 2004, there were approximately 10 million tube wells. I'm sure that number has doubled or tripled by now, which means that 50 to 60 million people were drinking water containing arsenic above 10 micrograms per litre. What does that mean? 10 micrograms per litre is the safe limit of arsenic in drinking water. And 32% of the 5 million tube wells so far tested by now there have been more tube wells tested, where above 50 micrograms per litre that contained arsenic. Give you a little bit more background to this so you can understand what these numbers mean. Now, this is a map of Bangladesh, and there is sort of good news, bad news here. The bad news is, of course, there is arsenic in the groundwater and high levels of arsenic, but the good news is that the concentrations of arsenic are not consistent throughout the Bangladesh. And depending where you are, and depending on how many wells, tube wells have been dug, and depending on the water flow, the concentration of arsenic does vary. Now, this has been really interesting, and scientists have done this amazing job of mapping out concentrations of arsenic all around Bangladesh, and this map gets continuously sort of updated. But there are 3 regions they've identified. The black regions is where the concentration of arsenic is below 10 parts per billion or micrograms per litre. So that's the safe level. The blue regions are between 10 to 250 parts per billion micrograms per litre. So that's starting to become unsafe because it's above the safe limit and quite a lot above. And then you've got the red regions, which is unfortunately majority, where it's well above the safe limit. In fact, it is 25 times above the safe limit. Now, what do I mean by safe limit? Well, the World Health Organization has determined that for drinking water, you cannot have more than 10 parts per billion or micrograms per litre of arsenic in the water. In Australia, we actually have a lower safe limit, and that is 7 parts per billion or micrograms per litre. So anywhere above 10 parts per billion or 7 parts per billion is considered as unsafe to drink that particular water. So you can see what I'm saying, how majority of Bangladesh has actually got levels that are well above. Now, by mapping out the concentration has allowed for a way to reduce people's exposure to the high levels of arsenic. And what they have done, which is quite interesting, is they've been able to determine which wells are safe to drink from and which are not. And the way they've done it is they painted the wells green colour if it was below the safe limit, or at the safe limit, but if it's above, the tube wells were painted red, so people would know and they could obviously not use that water. Now, the only problem is, as I said to you, the concentrations do change. So you can't just do one measurement and that's it. You have to be continuously testing the water and checking what the concentration of arsenic. All right, so how are you going to do that? Well, the most accurate and reliable detection methods use atomic spectrometric methods, and those methods require quite complicated and expensive instrumentation. So I'm going to throw some big words here. There's 3 instruments that can be used to detect arsenic. There's inductively coupled plasma, mass spectrometry, there's graphite furnace, there's hydrogeneration, atomic absorption. But basically what I'm trying to tell you is the fact that all these 3 instrumentations are quite expensive. They are complicated to use. I've got a picture here. This is this is one of our instruments that we use, hydrogeneration. Hydrogeneration is actually the most accurate way of detecting arsenic. It's the best way of detecting arsenic in water. It's quite a complicated way to do it. You have to generate an arsenic gas. Anyway, it's complicated and it requires a lot of chemicals as well. So these methods, as I said, are expensive, complicated to use. They need sophisticated equipment. They need access to gases. They need access to expensive chemicals. They require trained chemists. They require laboratory setup. This is not something that you can have in a little village in Bangladesh. And in fact, there are not many of these instruments available in Bangladesh. So you can't do continuous testing of these groundwater samples because these instruments are just not available. And if you send them to a major city, it will take, days and perhaps weeks to get the results. And in the meantime, people are drinking the water. So this is really not good for Bangladesh scenario. So is there another way we could detect arsenic that it doesn't involve such complicated instrumentation? And the answer is yes, there is. So this is where I come in. You can actually detect arsenic using electrochemical methods. And electrochemistry is an old technique. It is used to detect other metal ions, doesn't have to be just arsenic. And the good thing about electrochemical method is that it can use an instrument which is quite cheap, and most importantly, it is a field-based method. So just to give you an idea, this is a picture of the instrument that I've been using. It's called Portable Digital Voltammeter Instrument, and that uses electrochemical method. And it is very, very simple. All you need is 3 electrodes. I'm not going to go into the details, but the main electrode, the one where all the chemistry happens, is the gold electrode, solid gold, or you can deposit gold film. It doesn't have to be solid gold electrode. You can have a carbon electrode, which is cheaper. And you need an electrolyte solution, which is like the matrix, which you add to your sample. And I've developed a method that only requires a very cheap chemical, and that's ethanoic acid, which is a component of vinegar. So very cheap and very easy to use method. And as you can see, here's me in the back of a car, and I'm actually doing some arsenic measurements at a site in Perth, one of the sites that had large concentrations of arsenic in the groundwater. All right, so how does the electrochemical method work? So this is an area called voltammetry, and there is different types of voltammetric analysis. The one I use for arsenic is called anodic stripping voltammetry, and this is how it works. I've just simplified it for you in one slide. Here we've got a cup, so that looks exactly like this. So you've got a cup, and in that cup you place your sample, your groundwater sample, and you mix it with the electrolyte. So you're going to have lots of ions. So these coloured circles here are representing ions. Arsenic, there could be other ions in there as well. Chloride ions and whatever else is in the actual water sample. Now, what you do is you stir the solution just like that, make sure that the ions are evenly distributed, and then you make this working electrode, which is that gold electrode, that's where the electrochemistry happens. You make that very negative, you put a negative potential on it, and we make it actually minus 500 millivolts. And when that happens, look what happens. Ta-da! This is called deposition step. This is where arsenic 3+, or it can be arsenic 5+, is reduced because it accepts electrons and it's reduced to elemental arsenic, and it gets deposited on top of that electrode. That's called the reduction step, and that step can happen in 10 seconds or anywhere up to 3 minutes. You vary that depending on the concentration that you're expecting of arsenic in the solution. The next step is the following. Then what you do is you move the potential to a more positive value, for example, 50 millivolts, and that is when you have oxidation happening, or called the stripping step, and arsenic is oxidized, which means you form arsenic ions again, and you're releasing electrons, and those electrons get detected as current, and you then have the measuring step, and that's when you actually measure the current that's being produced. That's the whole method. And how do you link the actual current to the concentration of your arsenic? Very simple. You run a standard, so you make particular concentration. For example, let's say we make 50 parts per billion using a standard solution. We measure the peak that we get, the height of the peak, or the area under the peak. So for example, let's say we get 14 microamps, the height. So we know that 50 ppb has a height of peak of 14 microamps. If we then run a sample that we don't know the concentration of, and we get a peak of close to 14 microamps, we would say it's 50 ppb. Of course, you do a little bit more, you have to do a calibration curve and so on, but that's the idea. So very, very simple. There is a little bit more to it. You have to make sure you don't have any interferences, etc. But I've given you the gist. Now, there was a lot more that I did in this method, of course. It wasn't just a one day job. I've been working on it for quite a few years. I had to do a lot of testing, make sure that the method is linear. That means that the concentration of arsenic, the peak increases as you increase the concentration. So I made sure that I would increase the concentration and whether the peak, so if I double the concentration, does the peak height double? So I did that. I then plotted those values, and as you can see at low concentrations, so at the bottom here we've got concentration in parts per billion, and the vertical axis is the current. The lower concentrations are perfectly linear. You do get a little bit of adherence from the line of best fit at higher concentration, but that is to be expected. It's to do with saturation. You wouldn't actually analyze samples at 100 or 200 parts per billion. What you would do is you dilute the samples to fit in to this lower level. So it is definitely linear at lower levels. So the R-square value for all of these is 0.97, but if you go further down, if you only look at the lower concentrations, it would be close to 0.99, so close to 1, and that's what we've been expecting. I also looked at reproducibility. So if you run sample over and over again, does it give you the same results? And the answer is yes. Within less than 10%, we do get the same results. So there is a little bit of a drop in the peak. That's got to do with the fact that you've got ions in the solution, which will change the concentration of. But again, 10% accuracy is quite acceptable. I then looked at what's the lowest concentration of arsenic that I can detect, and I can easily go down to 5 parts per billion, and that takes 5 minutes to run that. But that is way below what you need to analyze, because remember the accepted safe concentrations of arsenic in drinking water for Australia was 7 parts per billion. So if I can go down to 5, that's more than I need to be able to detect. So that's good, isn't it? And actually, in summary, I can tell you that looking at what's happening around the world with the arsenic being detected in more and more countries, we do need a simple, accurate, reliable, and in-field, most importantly, an in-field method for detection of low concentrations of arsenic in water. The ASV method, anodic stripping voltammetry, could be the answer. It does have a detection limit of 5 parts per billion. I did also compare the results to ICP and AAS instruments, and they were spot on. I didn't show you that data. I'm also able to speciate between arsenic 3 and arsenic 5. So that's quite important because there are differences in toxicity between those two. So the results I got are very promising, and in fact the instrument has been implemented to be used in some parts of Bangladesh, but that's not part of something I'm involved in. The company that I worked for, they actually taken on that process, and that's their job to sort of implement the instrument. For me personally, the future plan is to obtain something called the National Association of Testing Authorities accreditation. It's quite a difficult sort of NATO accreditation. That means the method has been approved to be the accurate method for arsenic detection. That takes quite a while. It's quite an expensive process as well. Now, during the course of my research, I had a lot of support from the company, Modern Water, who are actually based in UK. They're based in Cambridge Science Park. B3 Company, who are based in Perth. They actually make the instruments, and I was involved in development of the instruments and improving the instruments. And I received quite a lot of research grants through Edith University. So that's it from me. My final words to you is to say thank you for listening.